Greetings, this is Mark Anderson for Kella Community College, and we are looking at part 2 of Session 2's video that talks about the shape of graphs or the shape of data. And today we're going to look at some more familiar graphs than we did in the last video. We're going to be looking at different types of bar graphs. We're going to look at some plots over time and then do some stem and leaf plots. So let's first of all tackle the two types of bar graphs that we're going to see in this book. And the first part is going to be the horizontal bar graph. And what we have are some activities here on the left-hand side. And on the right-hand side, we have calories burned by the minute. Because this barely fits on this page, I will not be scrolling down, and I'll be creating a new x-axis on these graphs. And I'll do so by taking my pen and just drawing it this way here. So that was going to be my x-axis for both of these graphs. Because what I want to show you is the difference between the horizontal bar graph and the Pareto chart. Now, the horizontal bar graph, horizontal means left to right, or right to left, and the bar graph is going to have spaces in them. Now, this information will not be given to you on the test that you will take, so you'll have to remember that horizontal bar graphs have spaces in them. And what I'm going to do is use some shorter words on the left-hand side here to denote my categories or activities. So let me just first of all write down activities, and then I'll use R for running and so on and so forth. Now, there are some discrepancies based on the books that they use, whether you go from high to low or low to high. I honestly would like you to keep them in one order or the other. I like to have them sorted from low to high or high to low, and I will do so from high to low in this case. So R will be for running. Cross country will be XC. That's the next most calories burned by the minute. And then we'll have tennis, and then golfing, and then bicycling, and then walking. On the x-axis, let's think about what scale we should use. It looks like we have to go from 2.8 to 14.5, so maybe an easy way to do this would be to go by 3s to get us up to 15. And we also could go by 5s to get by 15, but 3s will get us there just as easy. So 3, 6, 9, 12, and 15. So it's 15, 12, 9, 6, and 3. So running takes about 14.5, so I'm going to make a horizontal bar that goes almost to 15, so we'll kind of cut it off right about there. I got a little overhang there. Cross country is easy to measure because we have a tick mark exactly at 9, and you see that there are spaces between these bars right here. Then we're going to go to tennis, which is about 7.1, so it's beyond the 6. And golfing is going to be a 5. And biking's going to be 3.2, so just a little bit beyond the 3. And walking's going to be 2.8. So there's our horizontal bar graph. And now this Pareto chart, which is a vertical bar graph with no spaces between them, is going to make you think of a histogram, except that on the x-axis, instead of having a range of data values, we're going to have those categories. And I'm going to start high to low here. It might be easier to see that from the y-axis, which in this case, the y-axis is going to be our calories per minute, which I should have labeled here on my x-axis here, calories per minute. Let me do that so I don't forget. We'll go and use 15 again. So let's see if I can space this out nice. 3, 6, 9, 12, well, a little bit too far up at the top for 15, but again, we're freehanding this, and you're expected to do this by hand on the test, so there's room for human error here. We're now going to look at running, so that was about 14.5, so I'm going to make that an R for running. Let's see here, looks like we have cross-country skiing around 9, so we're going to put a little bar right there for cross-country and make my categories there down in the corner. These are going to be my activities. And then after cross-country, we have tennis. Tennis is going to be a 7.1, so we're going to make it like that. So tennis. Then golfing, which is 5. And then bicycling. Almost went up the chart. Bicycling was at 3.2. That's a little on the low side. Let me make that a little better. All right, so there's golf. There's bicycling. Oh my goodness. There's tennis and golfing. Sorry, my pen put an S there. Let's see here, and I did that. So let's put there for bicycling, and then we have walking. Walking is going to be right below the 3. All right, so it's a little sloppy, but it's pretty easy to read, especially when you can easily see how much the highest one had by its proximity to the y-axis. Now, again, some books and some people might say go from low to high, so it looks like a distribution that's skewed left instead of skewed right. But either way, just make sure that they go in order. All right, so let's take a look at the bottom chart here, where we're looking at continents and the number of roller coasters. Wow, that's great. I'm an avid roller coaster fan. This definitely piqued my interest, and I'm so lucky to actually live within driving distance of Cedar Point. But I would like to now take a look at this, and since again, trying to fit I'm going to make my x-axis here because it just won't fit on the screen. So there's my x-axis for both graphs. The category is here going to be, in this case, the continents. And I'll put that over here. And this x-axis here is going to be number of coasters. Look a little better. Number of coasters. All right, so I got my x and y axis done. Horizontal bar graph. Looks like we're going to talk about the highest one, which is going to be North America, or I'll just put NA. And after that is Europe, right there. And then after Europe, we're going to look at, let's see, the next one is, now there's a couple different letter A's there, so I'm going to go Asia with an A, lowercase s, and then S. Let's see, the next one is South America, so S-A, capital letters. And then after that, we're going to go Australia, A-U. And then after that is going to be Africa, so A-F. And if you want to make a little note to yourself on the side what these are, that's fine, but I'll figure it out. The homework's pretty straightforward here. And now if we're looking at a good scale to use, it seems like a pretty good scale would be to go by hundreds. And the reason why is because the highest is in the 600, 643, and some of these are in the lowest in the teens. So going by hundreds would make sense. So 100, 200, 300, 400, 500, 600, 700. So if I mark every other one here, it will be very easy for me to see what you used. All right, so North America being the highest, 643 roller coasters, probably more to come every single year. All right, so there we go, 643. Europe, not too bad. So 413. And let's see, now we have Asia with 315. I guess if I had time and opportunity and the body that could handle it, I'd love to ride all these things. SA, South America, and that's going to be at 45, so we have a way drop off here. And then AU for Australia, 22. And then Africa, 17. And again, these are just eyeball checks, but you really get a good visualization as to how that works there. So now just turning this 90 degrees practically, we're going to go by hundreds, 100, 200, 300, 400, 500, 600, 700. See, I did better that time by starting from the bottom up rather than starting from the top and hoping that I slice up the sections evenly. And that didn't do too bad of a job there. All right, so the first one is North America, and North America has around 643, so to the naked eye, 650 is probably going to be its estimate there. From there, we're going to go to Europe. Whoa, I wrote a 5 there. From there, we're going to go to Europe, and Europe is going to have 413, so and from there, we're going to Asia, so 315. And let's see here, then we go to South America. The big drop off there is South America, 45, so roughly it looks like 50. And then we're going to go to Australia, and Australia is going to have about half of that in the 20s. And then not too far behind is Africa with a little bit less than that. And so there are your graphs. All right, so the next type of graph we're going to look at is we're going to look at a time series graph, also known as the plot over time. The plot over time is really good to check to see trends. In fact, if you look at any progress of the stock market is pretty much all time series graphs, because you get to see the activity of either the Dow Jones or a particular stock in general, like maybe Apple or Google or whatever choice you want to make. You can see how it moves over time. Now, what we're going to look here is the safety records of the United States Airlines, and this is all sourced from the book that I got this from, and it's the number of plane accidents per year. So again, I'm going to have to kind of create my x-axis, since this will go off the screen if I scroll down further. So let me make an x-axis here. All right. And plot over time is literally what this is going to be. The x-axis is always some unit of time. In this case, the time are going to be in year, the year of which we get that data piece. So we're going to start in 1997. So I'm going to put this as 97, 98, 99, 2000, and then 2001, 2002, 2003, 2004, 2005, 2006, 2007. And again, just by sparsely labeling this, you can see that, oh, well, you're going by every year. Now, what I'm going to do is put a lightning bolt there, and this lightning bolt indicates that we're not going back to year 0, even though this will be 0 for the y-axis, which is the number of accidents. So from there, we are going to now go by single units, because it seems like our most terrible year in this data set is 2004. So that's going to be just going by ones. 1, 2, 3, 4. So this is pretty quick and easy to label all these. Now what you do here is you put a data point, a dot, corresponding to the year and the number of accidents. And there were none in 1998. And you do have to put the data point here. You just can't skip it. Which is a mistake I get sometimes, where people just say, well, there were no accidents. But you have to show that there was a drop between this year and this year. This is not a polygon, frequency polygon graph. This is a plot over time, since this actually just starts here and just continues on. Now, there were 2 in 1999, there were 3 in 2000, and you can connect these one point at a time, like I'm doing right here. You can get all the dots completed and then go from left to right. It's your choice. And I'm going to have 2001 and 2002 be the same. 2003 is 2. 2004 is 4, 2005 is 2, 2006 is 2, and then 2007 is 0. All right, so there we go. All of these beautiful tick marks. All right, there you go. There is your finished plot over time. And now what I will do is another example for you. This is the public debt in terms of, let's see, and I think some of the scale might be wrong in this. I do have to check here. This isn't in billions of dollars per family. We don't owe that many billions of dollars, so that's a little typo right there. I apologize. So this is the public debt in terms of dollars per family, according to the U.S. Department of Treasury from 2003 to 2009. Again, you can see that if I scroll down, it goes off the screen. So I'm gonna kind of use a little tick mark here to do this. Hold on. Okay, so there's my, this is going to be my years. Okay, so years, the year of that data point. So this is going to be at 2003. I'll put a little lightning bolt here. 2004, 2005, 2006, 2007, 2008, 2009. Question is like, well, how many do I really need to label? You should make it look good. I mean, if you only labeled 2003 and 2009, I think you're being a little lazy. If you label everyone, that's fine too. It's just this gets the point across. But in here, you'll note that the average cost of the debt per family, I mean, this is a really weird number. So you got to think, okay, if I'm going from 6,700 to almost 12,000, then maybe I should go by thousands. So this is 6, 7, 8, 9, 10, 11, gotta extend that a little bit, 12. So this would be, and what you should do when you label this here is you should not only label this as the average per family, but since I wrote down 6, that doesn't mean $6. That looks like famity. Family, thank you. Since this 6, which needs a lightning bolt since we're not starting at 0, this 6 doesn't actually stand for $6. This stands for 1,000. So in thousands. Or if you want to be a little bit more clever, you could put 6K, 7K, 10K, or 6K, 8K, 10K, or 12K, K meaning 1,000. Thank you, metric system. So we're now going to put our dots here. So it was just under $7,000, and then over that the next year, then almost 8, and then 8.5 the next year, 9 the next, and then 10, and then almost 12. So we have this gradual, basically exponential growth if you're looking at that. And if you want to know more about exponential growth, go look up some of my Math 125 or college algebra videos. But that right there is your plot over time according to this graph. And it's pretty straightforward, isn't it? But unlike the frequency polygon, you're not connecting it to the bottom. You're not making it look like a mountain. If there was a data point missing, like let's say there was no 2008 data for some reason, you connect 2007 to 2009. It just would show that kind of trend between the 2 years. So our final graph today, our final style of graph, is going to be the stem and leaf plot. Now the stem and leaf plot is created by, and believe me, a stem and leaf plot has its limitations. There is a great reason to use stem and leaf plots and a really good reason not to use stem and leaf plots. And I'll explain those at the conclusion of this. But a stem and leaf plot is created by a stem, which you would create and draw. And we're going to start to draw our tree on the left-hand side here. So here is our stem and leaf. And so this is the stem over here. The stem is always in the tens position. Tens. So you can see that the youngest president here at inauguration was in the 40s. So we're going to put a 4 there. So 4 stands for the tens. And then the leaf, so this is where all the leaves are. The leaves are in the ones position. So if we kind of scroll, if we just kind of like scan through here and try to look for the youngest president at inauguration, it's 42. So we would put a 2 there. So we'd read this 42. And I would cross that out so we don't look at it again, because each data point should only be used once. The next youngest president was 43. So we're going to look through, oh, look, 43 right there. So put a 3 right there for 43. Now, what happens is that you keep going through this list from low to high, and you keep adding up the data points as you go. Now, I want to kind of give you a little spoiler alert if we were to finish all these with presidents' ages at inauguration. The spoiler alert is that the fact that if you actually do this by fully tens, you're going to get really long leaves. And you don't really want that because you're not going to see a good range or distribution from it. So what the book is going to suggest, if they say, hey, if you've got a large set of data within one of the tens, you can split it up. So for example, this would represent any set of data from 40 to 45. Now, you'll note that there are no other presidents who were inaugurated at their 44th or 45th birthday. But there were 2 of them inaugurated at 46. And so I would cross out the 46s as I find them. All right, so the other 46 is here. And then there were 2 of them at 47. So there are 2 at 47, so cross out the 47, the other 47. And again, this is just methodical work. You're just going to take one number at a time, and once you find that number, and obviously since I'm looking at an answer key, I actually know what the numbers are without scanning through this here. But if I was to say, okay, the next number's 49, I've got 1 here, and I've got 1 here, so there are 2 49s here and here, and those are all of my 40s. Now again, this first row here was 40 through 44, and the second row here is 45 through 49. This would also, so 40 through 44, 45 through 49, 0 through 4 is 5 data points, and then 5 through 9 is 5 data points. Now, what I mean by that is that this second column here wouldn't start with a 5 because that would be lopsided. Because if you have, if you're counting from 40 to 49, the first 5 numbers would be 40 through 44. Count them on your fingers. You can see what I'm talking about here. Now, to save some time here, I'm not going to methodically go through this. I'm going to give you just the raw data from the answer key. This is going to be, there are 6, 1, 2, 3, 4, 5, 6 at 51. there were 2 at 52. Now you'll note when I make this, I try to line the numbers up. And then there were 1, 2, 3, 4, 5 at 54. 1, 2, 3, 4, 5 at 54. Now, starting at 55, there were 4 at 55. Okay, there's 4 at 50. Or sorry, 5 at, no, I wrote 5 of them. I should have only wrote 4. There are 3 6s. How evil. So 6, 6, 6. And then there are 4 7s. 1, 2, 3, 4. And then there's 1 8. And then in the 60s, we've got a 60 with 6 and a 0. 3 1s for 3 that were inaugurated at 61. Then we had 62. And then we had 64 and 64. And then 65 and 68 and 69. Now, these are the ages at inauguration. And now you're probably wondering, well, what's the purpose of a stem and leaf plot? Well, it's actually made a histogram. It's made a histogram where you can actually see all the data points. If you rotate your head 90 degrees, you can see that this is between 40 and 45. This is, start between 40 and 44, 45 and 49, 50 and 54, 55, and you get to see all the data points. Now, if I only used this, which was 40s, 50s, and 60s, then the graphs, and I'm not writing down all the numbers, but they would have, looked something like this, and you wouldn't see such a dynamic curve or this symmetricness of it with only just 3 rows. So that's the reason why they split those up, and you'll see those in the answer keys or the solution manuals why they did that. Another cool thing that we're going to get to in the next unit is we're going to start looking at outliers. So as we hit presidents who are in the 70s, we get to actually look at, is 70 an actual outlier or not, or if somebody was in their 30s, would that be an outlier? Because outliers are actually determined by the spread in the center of a data, usually by quartiles in this case with the box and whisker plot. But that's for the future. We can look at that and get all deep in the data. So let's do one more stem and leaf plot to close this off, and you'll see that now we've got how many calories are in these non-fat-free salad dressings. All right, so here we go. We're going to take a look at the calories in these salad dressings. All right, and I'm going to now have to do just a little bit of thinking, because if I'm thinking about this here, I've got to create my stem and leaf plot, and I got to think, okay, my stems are in the 10s. So it looks like my lowest number is 100. So that is going to be 1, 0, and this is going to stand for the hundreds column. Now, I'm not going to need to split this up, so I can just go by tens. My highest calorie count is in the 90s, so we have, this is 110s, 120s, 130s, 140s, 150s, 160s, 170s, 180s, and then finally 100, anything in the 190s. So you can see that there are 5 in the hundreds. So there's 1, there's 2, there's 3, there's 4, and I missed 1 right there, 5. So 5 zeros, which indicates that if you don't have any data points, you don't put anything down, because a 0 indicates a data point, in this case the hundreds. There are 2 at 110, and if you're closely looking here, there's 1 of them at 115. So I put a 5 there, and that means 115. I'm going to quickly finish this up here because I can go through the toil with you, but I think you get the gist of this here. I had 6 at 120. I had 5 at 130. I had 4 at 140. And 5, 5, 5, 5. And then I have 3 at 150. And then I have 6. And then I have 1 here at 170, 2 at 180, and then 1 at 190. Now you can see that this distribution is definitely a lot different than the symmetric distribution of the president's ages at inauguration. So here, if you look sideways, you can see that this is not really symmetric, a little bit more skewed to the right. There's a lot more data points on the lower end than the higher end if you looked at your head 90 degrees to the right. And you can actually see the data points. So why don't we use scatter plots all the time? And the reason why we don't use them, boy, this sounds like a pretty good test question, right? The reason why we don't use scatter or these stem and leaf plots all the time is because if you have a very large data set, that this is very cumbersome. Or if your data set isn't in a very easy to produce format, like in this case 10s and 1s. You would have to do a lot of rounding to work out a problem that was in the thousands or the millions, and by then you just use a scatter or use a stem and leaf. Sorry, excuse me. You use a histogram, not a scatter plot. That's for a whole nother chapter. But we are going to use a histogram most of the time because it's the most flexible, but you can't actually see the data points. Here you can. So that concludes all the different types of graphs that you will be tested on, and I do appreciate you watching the videos. Thank you very much, and good luck working on those by hand, and thanks for watching.